Okay, so last time we found our normal ordered Hamiltonian, this thing, and we discussed the vacuum or the ground state of the Klein-Gordon field. And now we want to move on to talk about excited states. And so our excited states will just be, in the ordinary quantum mechanical harmonic oscillator, we found the excited states by acting the raising operator on the ground state. And so we're going to do the same thing here. And we're going to want to know, what is the energy of those states. And to find that, we're going to need this commutator between the Hamiltonian and the raising operator. So let's just work that out first. So it's this. Again, notice I'm using P for this operator here. So when I'm writing out my Hamiltonian, I don't want to use P as a dummy variable. I want to use something else. So I could use Q. I just picked P prime here. So if you write this out, this minus this, or this times this minus this times this, you'll just get this. I can move this operator inside the integral because this is P prime, this is P. So I'll just get this, and then I can, so I get these two terms, and then my A daggers commute for any value of P, so I can move this A dagger P prime to the left, and then you'll see that I can factor that out, and I'll just be left with AP prime AP dagger minus AP dagger AP prime. So in other words, I'll be left with the commutator of AP prime AP dagger. And that's good because I can use our commutation relations to get a 2 pi cubed delta of P minus P prime. And that will enable us to evaluate this integral. And so I'll just get omega P AP dagger evaluated at P. So not too bad to work that out. And similarly, you can work out for the lowering operator, the commutation relation will be this. So now that we have that, we can work out. So our excited state, if we have A dagger acting on the ground state, that will be an excited state. And we want to know what is the energy of that state. So to find the energy of that state, we're going to act the Hamiltonian on the state. And so to compute this, we will commute our Hamiltonian past A dagger and use our commutation relation, and we'll get this. And then, so these two terms here, so H acting on the ground state is 0, so we've defined the Hamiltonian to do that, and we'll just be left with omega P times our excited state here. So in other words, our excited state has an energy omega P. And then if we remember, our omega P was just square root of P squared plus M squared. It's the energy of a relativistic particle with momentum P and mass M. So based on that fact, we're going to interpret the state as a one particle state. And again, it has energy of this and momentum P. So we can also define a momentum operator. So just like, to find the Hamiltonian, we took the classical Hamiltonian of the Klein-Gordon field and then quantized it. And so using our expression for the classical momentum operator for the Klein-Gordon field, we can quantize, we can write expand our fields in terms of raising and lowering operators, just like we did with the Hamiltonian. And that will involve a lot of, cancer math, like we saw when I worked out the Hamiltonian. But it's, if you can do that, you can do this. So I'm not going to go through it all. But basically, after you normal order everything, you will get that the momentum operator is this. And One convenient thing to notice is that this operator is almost exactly the same as our Hamiltonian operator. The only difference is that instead of omega p here, I have p. And that's useful because it means our commutation relations will just be, we don't even have to work those out. They will just be the same thing here, only with omega p replaced by p. So p, the commutator of p with a dagger is p a dagger, and similarly for the lowering operator. And so we can just immediately say that, well, the eigenvalue, the momentum eigenvalue of our one particle state is just p, which is what we would expect. And again, it's consistent with our interpretation of this operator creating a particle of momentum p and hence energy omega p. And then obviously we want to know, well, what about a two-particle state? So if we have, if we create two particles, one with momentum p, one with momentum q, what is the energy of that state? And so now you'll just have to work out, again, you just use the commutation relations that we found before, only you have to do it twice now. Well, anyway, you can work it out, as you see here. The point is that what you get is the eigenvalue of this state is just omega p plus omega q. So it makes sense. The energy eigenvalue of this two-particle state is just the sum of the energies of the individual particles. And similarly for the momentum, obviously p acting on the state, we would just get p plus q. So the momentum is just the sum of the momenta of the individual particles. And of course, we can generalize this to n particle states. If we have n particles with momenta p1, p2, all the way to pn, then the energy eigenvalue of that state will just be the sum of those energies, and similarly for the momenta. And the last thing we can do is define another operator, the number operator, and it's going to look almost exactly like our Hamiltonian momentum. The only difference being instead of, in our Hamiltonian we have this kind of form with omega p. With our momentum operator, it's the same form, only with p. With our number operator, it's the same thing, only with nothing. Well, with 1, basically. And so we can immediately say, well, if the Hamiltonian acting on an n-particle state is this, and the momentum operator acting on an n-particle state is this, then the number operator acting on an n-particle state will just be 1. And so instead of omega p, instead of p, it's just 1. So I'll get a 1 plus 1 plus 1 plus 1 all the way to n. So I'll get n ones, which is n. So basically the number operator will tell me the number of particles in the state.